So we've been talking about gas mixtures and partial pressures. The air that we breathe is a mixture of gases, and oxygen is the gas that we need. Our lungs perform best when the oxygen has a partial pressure of 0.21 atmospheres, which is what the air has at sea level. At higher elevations, the total pressure is less, and so the partial pressure of oxygen is less. And that's why when you go to higher elevations, you tend to get out of breath more easily because there's just not as much oxygen for you to breathe. We have a word for not getting enough oxygen. It's hypoxia. Hypo is that prefix that means below or less, right? So hypoxia means not enough oxygen, oxygen starvation. Severe hypoxia happens at a partial pressure of oxygen that's less than 0.1 atmospheres and can result in death because basically you're suffocating, you can't breathe. So hypoxia is bad, but you can also get too much oxygen. So as with anything, not enough, bad, too much, bad. There's a happy middle, even for things like oxygen and water. So the range of safe oxygen levels is quite large, from just below 0.21 up to about 1.6. Beyond those extremes, then your body is not going to function as well. So above a pressure of 1.4, you get oxygen toxicity. Symptoms include twitching, tunnel vision, convulsions. So when might this happen? Well, you're not going to run into oxygen toxicity just, walking around Fresno. It's not going to happen. It's going to be an artificial situation. Breathing pressurized air, such as when you're scuba diving. You breathe pressurized air at too high of a pressure. The higher the total pressure, the higher the partial pressure of oxygen, and then you could get into oxygen toxicity. At the surface, the total pressure is 1 atmosphere, and so the partial pressure of oxygen is 0.21. So oxygen is 21% of the air, and so 21% of the total pressure is from oxygen. If you go 30 meters below the surface of the water, every 10 meters the pressure increases by 1 atmosphere. So now you've got a total pressure of 4 atmospheres. That's the pressure that the air has to be under so that you're able to breathe at all. Now the oxygen partial pressure has gone up to 0.84 atmospheres. So it's definitely much elevated. You keep going lower and breathing pressurized air, and then you can get into oxygen toxicity. Well, there's also increased partial pressures of the other gases in air, and nitrogen is the main component. So too much nitrogen can be bad for you as well. It's called nitrogen narcosis or rapture of the deep. Apparently it feels similar to being a little bit drunk, which may not seem like a horrible thing, but if you're several meters below the surface of the water, you don't really want to have impaired judgment, do you? So that can be a bad thing. So a deep sea diver is going to need to use a pressurized gas other than air, because at those high pressures, the nitrogen level is too high and the oxygen level is too high. One mixture is heliox, a mixture of helium and oxygen. So that doesn't have any nitrogen in it, so you can't get nitrogen narcosis, and you can control the level of the oxygen by how much helium is mixed in there. Bless you. Also makes you talk funny, but since you're underwater, nobody can hear you, right? So we could look at a question like this based on our knowledge of partial pressures. A diver breathing heliox with an oxygen composition of 5% wants to adjust the total pressure so that his partial pressure of oxygen is 0.21 atmospheres. What should the total pressure be? So we want to have a partial pressure of 0.21. So PO2 is 0.21 atmospheres. The oxygen composition is 5%. So with gases and partial pressures, we convert that into a fractional composition. You divide by 100%, And so that means that 0.050 is the fractional composition of the oxygen. 5% of the gas is oxygen. 5% of the total pressure will be the oxygen partial pressure. So we want it to be 0.21 atmospheres, and that's going to be 0.050 times the total pressure. I'm used to teaching this in Chem 1A where they actually have an equation for this, and so this is a little tricky for me sometimes to explain it without the equation. Does that make sense, though? 5% of the total pressure, so 0.05 times the total pressure, this is what we want. So that means that the total pressure must be 0.21 atmospheres divided by 0.050. So 0.21 divided by 0.05. So 4.2 atmospheres is what you would want the total pressure of the gas to be, the heliox that you're breathing. Any questions? Collecting gases over water, another application of gas mixtures. This is what we did in lab yesterday. Slightly different setup, but same idea. So here they've got zinc and hydrochloric acid, and that undergoes a reaction very similar to what we did with the magnesium, generates hydrogen gas. The hydrogen gas expands and is trying to escape, and so we're directing it here through this tube and into this inverted jar that was originally filled with water. And as the hydrogen bubbles in here, it occupies space and displaces the water. So what we have above the water is the hydrogen gas that we've been bubbling in there, but we also have water vapor because the water evaporates. Because the water evaporates, and so we've got some water vapor in there as well. We have a mixture of water and hydrogen gases. We call that a wet gas. How much water vapor is there depends only on the temperature of the water. And so that's very convenient because it's actually a little bit tricky to measure directly, but we don't need to. If we know the temperature of the water, we can just go look up what the partial pressure of the water is. So there are tables like this. This is not very detailed. It just gives us every 10 degrees, except for this 25 in here. But when we're given a temperature, we can look up what the partial pressure of the water is. So hydrogen gas was collected over water at a total pressure of 758 millimeters of mercury and a temperature of 25 degrees Celsius. What's the partial pressure of the hydrogen gas? Well, this is just Dalton's law of partial pressures. So the total pressure equals the pressure of the hydrogen gas plus the pressure of the water vapor, the water gas. Water gas sounds funny. So that means that the partial pressure of the hydrogen is the total pressure minus the partial pressure of the water. Our total pressure is right here, given to us, 758 millimeters of mercury. To find this partial pressure of the water, we just look in the table. We're given a temperature of 25 degrees, and so the partial pressure of water at that temperature is 23.8 millimeters of mercury. So the partial pressure is the total pressure, 758 millimeters of mercury, minus 23.8 millimeters of mercury. This one is, the concept here is so simple that people tend to have trouble with it because they think, oh, it can't be that easy. There must be some trick to it. No, it's just adding and subtracting. Maybe the trickiest thing is making sure you've got your units the same.
Will we need to convert to atmospheres, or if it's already given, then just leave it?
In a question like this, you do not need to convert to atmospheres. If you need to use the pressure in the ideal gas law, then you have to convert to atmospheres. So we do the subtraction, and then let's review our significant figures. When we're subtracting, we're looking at number of decimal places. So this one ends in the ones place, this one ends in the tenths place. And so the last significant figure is in the ones place. If this is a final answer, we're going to say it's 734 millimeters of mercury. Any questions?